Hello and welcome again to Principles of Reinforced Concrete, and for today's meeting we would be discussing about short columns under axial load with uniaxial bending. Okay, so last meeting or last video we have discussed there the analysis and design of your concentrically loaded columns. So when we say concentrically loaded short columns, it means that you are only to analyze short columns under axial load. So that is for concentrically loaded columns. So this time, as you can see in this slide or in this video, that we will be discussing about the combination of your axial loads and your uniaxial bending. Okay, so what is uniaxial bending in the first place? So when you say uniaxial bending, or let's say when you say bending, this of course results from flexure. So flexure. And for you to have a flexure, it must have moment. And in this case, this moment should be a bending moment. So bending. So I presume that you are already familiar with this term if you are watching this video. Okay, so that is for bending. But what about for uniaxial? So uni basically means one, and axial basically means axis. So collectively, the term uniaxial means one axis. So trivia guys, so when you say biaxial, so bi means two, axial means axis, so two axes. So when you say triaxial, so tri means three, axial means axis. So this means three axes. Okay, so enough of that. Okay, so let us go back to the term uniaxial bending. So collectively, when you say uniaxial bending means it is to be bending in one axis only. Okay, so in this term here, in this figure here at the middle part, so let's say that you would be having, of course, your P. So your P is basically your axial load. And you would be having a certain moment here that is only about one axis. So if that is to be the case, this two right here is to be your axial load with uniaxial bending because it is only bending in one axis. And as you can see in your right, so in this photo right here, so by the way guys, I got this photo from the structural.org. Anyway, so proceeding guys, as you can see, we would be having two moments here. So we have here your mx and your my. So it means that you would be bending along, about the x-axis and about the y-axis. So with that guys, since it is to be bending in two axes, this is what you would be calling your biaxial bending. Okay, so there. Okay, so how can we solve for this? So by the way guys, if we are to draw, let's draw a certain column. So let's say that this is to be a column. And let's say that its centroid is to be located here. So let's say, So let's say that this is to be the centroid or the neutral axis of your column. And if you would be placing your load here, so let's say that this is to be your load. If it is to be concentric, it means that it is only subject to Pn or it is only subject to axial load. But what if, let's say your load is to be located here. So as you can see, it already has its own eccentricity. So this is now to be its eccentricity. So let's say that is to be E. So let's say that this is to be your x direction. So this is now to be eccentricity x. So there, and you would be having, of course, your Pn. So your Pn times Ex, this is basically equal to your moment. So force times lever arm, that is now to be your moment. So if it is to be having a certain moment, so its result is to be, of course, it would be having a certain moment Mn. And with that, guys, as you can see, this is now to be a flexural member. So if this is now to be a flexural member, so for example, that this is to be the section of your concrete or your reinforced concrete column, if this is once again subjected with flexure stress or moment, this is now to be considered, you can now consider this as a beam. So your beam are flexural members, of course. And in this case, guys, as you can see, if this is now to be your moment Mn, you would now be having some compressive members, or I mean compressive fibers, and you would now be having a tensile area or tensile fibers here. So basically guys, if this is once again your section, so if this is to be your section, you can actually rotate it in this manner and consider it as a doubly reinforced beam. Oops, I'm sorry. So this is now to be a doubly reinforced beam. Whereas, let's say if this is to be your moment, it means that this part here is to be under compression. So let's say that this is now to be your, let's say your compressive concrete. So with that, that is now to be equal to 0.85 FC prime AB. And as for this, so let's say that this is to be your AS1. Let's say that this is to be your AS2. So that should be multiplied with FS1. So by the way, guys, I would just be drawing its stress diagram for it to be more presentable. Okay, so if this is to be the stress diagram, of course, this is now to be the stress due to concrete compression. So once again, this is to be 0.85. Just be writing it here. So 0.85 FC prime AB. Whereas for the value for your A, so this is to be your A is to be equal to betas of 1C. Okay, and we also have here your tensile bars. So it is now to be directed here. And you also have your tensile bar here. So this is now to be equal to AS1, FS1. So let's say that this is to be your AS1 and this is to be your AS2. And this is now to be AS2, FS2. And do not forget, guys, that you still have your compression bars. So with that, your compression bars would now be located here and located here. Sorry. Okay, so this one is to be your AS1 AS1 prime, FS1 prime, and this is now to be your AS2 prime and FS2 prime. And once that you already know this, you can actually solve for it already using the principles of doubly reinforced concrete. But by the way, guys, I have just rotated this once again. So its real orientation is to be like this. So what you would be doing is that once again, you would be rotating this. So with that, so copying this to our next slide. Okay, so if you would be solving for, if you would be analyzing your columns, of course, you must know the value for your PN and the value of your MN. And of course, the value of your E, of your eccentricity E. Okay, so like a while ago, so just like what I said, your MN is basically equal to PN times E. And as you can see, this is already one equation. So PN times E. So how can we get the value for your PN? So for us to get the value for your PN, let us just get the summation of forces vertical. So the result here, so the result of your summation of forces vertical, that is now to be your PN. So with that, guys, so considering this, for example, so your PN is now to be equal to, so let's say that the forces going up is to be positive and the forces going down is to be negative. So with that, guys, let's say that this is now to be 0.85 FC prime AB, then plus AS prime, FS prime. So let's say that you would be having two layers. So let's say that that is to be AS1, FS1 prime, plus AS2 prime, FS2 prime, etc. But generally speaking, just add all of the AS and FS prime. So there. So ito, generally speaking, let us just write it this way. But once again, if you would be having multiple layers, of course, you must add all of them. Okay, so there. But as a representation of our general formula, I will just be writing it this way. Okay. So that is for your forces going up. But what about for your forces going down? So that is now to be equal to AS, F, S. So there. So once again, if you would be having multiple layers, so this is now to be AS1 FS1 plus AS2 FS2 plus AS3 FS3, etc. But once again, generally speaking, it would now be like this. But as you can see, guys, in this equation, we have two unknowns. So we do not know the value for our Pn, and of course, the value of our Fc prime, our B, and all of this can actually be solved. But once again, we do not know the value of our A. So we have two unknowns in one equation. Okay, so let's get the summation of moment. Let's say that is to be the summation of moment about this point, or CL, or the center line. So by the way, guys, if for you to get the moment or the moment capacity, you can actually get the moment about any point. But in our lesson for today, I advise you to get the moment about the center line. Why is that the case? Because once again, your Mn is to be Pne, and the value for your eccentricity is measured from the center line. So if you would be getting the moment about any point, so magsosolve pa kasi kayo. So you would still be solving. So once again, your E, so let's say that this is to be the location of your force. So let's say that this is to be the location of your Pn, and this is to be your center line. This location here is to be your eccentricity, and that is to be in reference with your center line. So once again, I advise you to get the moment at the center line, but of course, it would be up to you. Okay, so for the moment about your center line, of course, this is now to be equal to your Mn. So with that, guys, so this is to be equal to, of course, your 0.85 Fc prime AB. So 0.85 Fc prime times AB. Of course, you must multiply this with the lever arm. So what is to be the lever arm? So if you are to get the moment about this location, which is to be in the center line, and let's say that this is to be your compression area, for example. If that is to be the compression area, your lever arm must be measured from your center line up until the center here. So let's say that this is to be for the value of your H. Let's say that this is now to be the value for your B. So for that one, so let's say that once again, you would be getting its centroid. This half here is now to be H over 2. So if that is now to be equal to H over 2, so once again, this is now to be equal to H over 2. Oops, sorry. And this is to be, let's say, A over 2. So with that, this is now to be H over 2 minus A over 2. Okay, so what about for your AS prime, FS prime? So, by the way, guys, if you would be getting the moment about the center line, so I would just be rewriting this to our next slide. So if you would be getting the moment about this point, which is to be the center line, all of them are going counterclockwise. So if this is to be your lever arm, this force is to be going counterclockwise. This force is going to be counterclockwise. This force is going counterclockwise. This force is also going counterclockwise. And this force is also going counterclockwise. So with that, all of our parameters here would be positive. So let's say counterclockwise positive. So CCW positive. Okay, so with that, so plus AS prime, FS prime times lever arm. Okay, so if this is now to be your AS prime, your lever arm would now be, so if this is now to be, of course, half, and this is, of course, half of the total depth, and that is to be H over 2. So if this AS prime here, of course, it would be having its spacing of D prime. So that is now to be equal to D prime. So the lever arm from your center line up until the centroid of your bars is to be H over 2 minus D prime. So H over 2 minus D prime. Okay, and as for your still rebars at the tension side. So I would just be writing them at the bottom part since we do not have any space here any longer. So plus AS times FS times lever arm. So it would be up to you on how you would be drawing the lever arm. You can also be writing it this way. So H over 2 minus D prime if you please. So H over 2. So this is also H over 2. And this is, I presume that the D prime here is also equal to the D prime here. So I assume that this is now to be, they are to be equal. But if you do not want it to, if you do not want to draw it that way, so this is now to be your D. Of course, if from the compression side up until the tension side, if you can remember, that is to be your DT. So from the analysis of reinforced concrete beams, so DT yung tawag dyan, yung distance from the outermost compression fiber up until the centroid of your outermost tension bar. So that is to be DT. So with that, if this is to be DT, so your lever arm here is to be DT minus H over 2. So that is one among many formulas that you can use for your tension bars. So I would just be using that. So once again, the whole of this is to be DT, and this is now to be H over 2. So for you to get this lever arm, that is once again H minus, D minus H over 2 or DT. So depending, if it is only one layer, that is basically just D. But if it would be having two layers, that should be DT. Kasi kapag two layers siya, the value for your D is to be the centroid. And if one layer siya, yung centroid mo is exactly DT. So D is equal to DT if it is to be one layer. Okay, so by the way, so just for our general formula, that is now to be equal to, so H over 2 minus D prime, or you can also write it as H D T minus H over 2. So whichever pleases you, and whichever would make your formula easier. Okay, so that is for our moment and our PN. But as you can see here, for this equation, so for our equation here, we have plenty of unknowns still. Okay guys, so as you can see that these principles came from the analysis of your doubly reinforced concrete beam. And as you can remember, it is very simple, except for this one, it is, well, not that direct. So what I mean here is that, of course, so let's say that if you would be using this formula right here, so this is actually unknown, guys. Of course, you would be solving for this. However, in this formula, this is also unknown. So the value for your A is to be betas of 1C. So it means that it is to be dependent upon the value of C. As well as for your Fs prime, so this is to be dependent upon the value of your C. And for your Fs, so this is once again dependent upon the value of C. So in this equation, we have two unknowns. As well as for this equation. So Mn, this is unknown, as well as for the value of your A, and all of the parameters here that is to be dependent upon the value of C, which you do not know yet. So previously in the analysis of the analysis of doubly reinforced concrete beams, before we do not have Pn here. So we do not have an axial load. So before, this is basically equal to 0. So if that is to be equal to 0, you can actually solve for the value for your C in this equation already. That is before. But right now, that isn't to be the case because we now have a value for our Pn here. What is to be our approach in solving for the values of your Pn and for your Mn? Okay, guys, so if you are to talk about these kinds of problems, so if you are to tackle about these kinds of problems, in most cases than not, your eccentricity is already given. So there. Okay, so proceeding. So how can we solve for, let's say, our Mn and our Pn if we cannot use these equations directly? Our approach here is that we will be assuming the values of our C So we will be assuming the values of RC and we will be solving for PN and MN. And we can know that our assumption is correct if this equation would now be satisfied. So once again, we will be assuming the value for your C, then solve for PN, assume for the value for your C, solve for MN, and using this equation, you will be checking if it is to be accurate already. Okay, so once again, assumption. So what is to be our basis for assumption? So there is this thing which we call E-balance or the eccentricity balance or the balance eccentricity. So if you can remember before, for your raw balance, so for your rho B, this is to be the steel ratio that would give you a value of Fs exactly equal to Fy. So if you can remember in our boundary for your compression controlled and your transition zone, so that region or their interface is to be Fs is exactly equal to Fy. So with that, this is now to be your eccentricity that would ensure that your outermost tension rebars would actually fail. So there. Okay, so how can we solve for our E-balance? So once again, we would be goaling for our E-balance to be solved. So once again, pangalawang once again yan. So twice again. So once again, how can we solve for our E-balance? If we would be assuming C here, so for your E-balance, we would now be solving for C balanced. So how can we solve for C balance? So if you can remember from the previous discussions, this is basically 600 divided by 600 plus Fy times the effective depth D. So there. And after solving for your C balance, you can now solve for your nominal P or balanced axial load. So that is to be PNB. And that is to be equal to, so just substitute it here. Substitute the value for your C balanced here. So, by the way, before you can solve for PNB, you must solve for Fs prime and Fs first. But of course, for your balanced condition, Fs is now to be equal to automatically Fy because that is to be your balanced condition. But if you do not believe yourself, you can actually solve for it. But of course, you must the answer here must be Fy. Okay, so for the respective equations, so for your Fs prime, you should already know this. Once again, in the analysis of doubly reinforced steel bars, doubly reinforced concrete beams. So this is to be equal to, so 600 times C minus D prime divided by C. So there. And for your Fs, this is to be equal to, so 600 times D minus C divided by C. But take note that your answer here should be equal to Fy. So Fs must be equal to Fy if the C that you will be using here is to be your C balanced. Kasi same equation lang naman itong dalawa. They are just simplified and they are just cross multiplied, etc. Okay, so after knowing your value for your Fs prime and Fs, you can now solve for the value for your P and B and your M and B. So there. So you can solve for Pn and Mn using the C balance that you have solved. And after solving for your PNB and MNB, so check natin dito. So check. You will now be solving for E. So how can you solve for the value for your E? Or your E balanced? So PNB, MNB, so you will be resulting to an answer of E balance or the balance eccentricity. So if you can remember here, so Mn is actually equal to Pn times E. So there. And with that, so note, so Mn once again is to be equal to Pn times E. So with that, MNB is to be equal to PNB times EB. So cross multiplying, your EB is now to be equal to, MNB divided by P and B or P balanced. So there. Okay, so your question is, so why did we solve for this? So guys, so if let's say that this is now to be your section and you will be arriving at a certain balance eccentricity. So let's say that the balance eccentricity that you have solved is to be located here, just for pretend. And of course, your centroid is to be located at, of course, the centroid, the neutral axis. And with that, this is now to be for the value for your E balanced. So E balanced. Okay, so once again, your E balance is to be the eccentricity that would ensure that this steel right here, or the outermost steel bars, would now yield. And there. And let's say that the given eccentricity in the problem is to be less than EB, or if it is to be located here, for example. So, for example, that it is to be here. It means that your column is to be compressive controlled, or a compression controlled. So let's say that this is to be E, this is now to be compression controlled, if you can remember before. And let's say that if your E is to be located here, which is to be greater than your EB, of course, it is not to be compression controlled any longer because this one would yield. So, kind of tension controlled. So, there, tension controlled, and what you call this? Since your steel rebars would now yield. Okay, so with those taken into consideration, let us now, by the way, I would just be moving them here. I would now be making some conditions here. So if your eccentricity E is to be greater than your balanced condition, or your balanced eccentricity, it means that of course your Fs would now yield, or Fs is now to be greater than or equal to Fy. But since Fs cannot be greater than Fy because this is to be the strength of your steel, this is now to be equal to, so Fs is to be equal to Fy already. So that is to be the condition. And if that is now to be the case, so your C now is to be less than C balanced. So as you can see guys, baliktad siya, no? So they are to be the other way around. So there. And if your E is to be less than your E balance, which is to be the case here, which is red, it means that your Fs, or your tensile steel, did not yield. So with such, Fs is now to be less than Fy. So from that guys, you will now be solving for your Fs in this manner. So solve for Fs for you to solve. Okay, so Fs is to be less than Fy. So with such, your C is now to be greater than your C balanced. Kasi imagine yun, no? So imagine that your force would be here. Of course, your compression would now be bigger. So let's say like this. And let's say that your eccentricity is to be, well, big. It means that your compression steel, your compression concrete would now be little. Thus, your C is now to be smaller. Okay, so what is to be the importance of us solving for this? Okay, so if you can remember guys, that for us to solve for Mn and Pn, we must have some assumptions. Okay, so if this is to be the case in your problem, in your assumption, your C should be less than Cb. So this is just to be basis on what C you would be assuming. You must assume a C less than Cb if your E is to be greater than Eb. Or let's say that your E is to be less than Eb, your C must be greater than Cb. So this is just for the basis of your assumption. For pretend that this is to be the case, so you will be assuming up until you arrive at this equation, or let's say that if you would be arriving, you would be satisfying this condition. Okay, so that is to be it. So I will be showing you a sample problem in the next video. So there.